Imagine you send your pet monkey on a rocket ship to a faraway galaxy. The ship will travel at the ship will travel at a speed of 0.8 c, which is 80% of the speed of light. Let's say there's a light clock on the rocket ship that the monkey likes to stand on. You'll stay behind on Earth as shown. Assume you have an identical light clock next to you on Earth. Only the monkey's light clock is pictured below, though. And just for simplicity's sake, let's assume a non-accelerating Earth. A light clock can consist of mirrors and a light beam. The light beam is emitted from one side, goes up, strikes a mirror on the other side of the clock, and then comes back. When it comes back, 1 second of time is registered. 2 reference frames are drawn below. First, there's the reference frame of the monkey. Let's call that frame S. It is the moving frame. It is the frame that's moving at 0.8 c relative to the person on Earth. We can also draw the person on Earth's frame, and that can be called S prime. So in our reference frame, S prime, we see the monkey as moving. But according to the monkey's frame, frame S, we're the thing that's moving. Both frames have to be drawn in order to explain Einstein's relativity. In the monkey's frame, the light beam simply goes up, strikes the mirror, and goes back down. This is the shortest possible path for the light to take. It's traveling at a speed c, and it takes time t for this to happen. Now, technically, that time t is TO. It is a proper time as measured by the monkey. The person on Earth can't measure the proper time because they're not in the reference frame of the clock. Now let's move over to the person who's standing on Earth's reference frame. According to them, the clock is moving, so the light actually takes this longer path where it goes diagonally, strikes the mirror, and then comes back. This path is longer, and light still has to travel at speed c to all observers in all reference frames. So, what is the distance now? It's not ct anymore. It's ct prime, where t prime is a time that's measured by an observer who's not in the reference frame of the clock. This demonstrates why time is different for these different observers. One of them is longer than the other. This effect in relativity is called time dilation. If you're not in the frame where an event is occurring, then you would measure time to be longer than it actually is. Okay, let's try to answer the questions. From your perspective on Earth, does the monkey's light clock appear to run slow? Would it read the same time as your clock? Or would his clock actually run fast? Which one do you think it would be? So the monkey is going to experience time as normal time. And that's going to be the shortest time that could possibly occur. So by the time his light beam would have already struck his mirror, from our perspective, the light wouldn't have got that far. So he couldn't register a second in our reference frame as quick as he could in his own reference frame. This means that we're going to perceive his clock to actually run slow compared to our clock. I mean, think about it. If we have a clock right here that is not moving compared to one that is, then what will happen? That beam will have already struck the mirror before the light beam strikes the other mirror on the monkey's clock, which means when it comes back down and registers that second on our clock, it wouldn't have got that far on the monkey's clock. So his clock is going to run slow according to us. But what about from the monkey's perspective? will he think that our clock runs slow? Will he think our clock reads the same time as his, or would he see our clock as running fast? Well, in order to demonstrate that, you might show what our clock looks like from his perspective. In his perspective, we're moving away from him. So our clock is going to move away from him too. And that means that light will take the diagonal path for our clock now. But the light won't get all the way to the other side in the same time that it does for him. So he's going to believe that our clock runs slow. And there's symmetry to that situation. After 10 years on your clock, the monkey reaches his destination, and according to you, is the monkey 10 years older than he was but hasn't aged hardly at all? Is the monkey 10 years older than he was and he actually looks 10 years older? Or would the monkey be 10 years older than he was and look much, much older? So all the biological processes that happen inside the monkey's body have a relationship to the way that light propagates. If we see the clock slow down, we're going to also see the aging process for the monkey slow down as well. And so even though we'll record 10 years on our clock, for the monkey, he hasn't aged 10 years. Because the processes in his body haven't taken place like they normally would. Finally, when the monkey reaches his destination, according to the monkey, does he think that more than 10 years have passed since he left? Does he say that 10 years have passed? Or would he say that much less than 10 years have passed? Well, as you can see in our reference frame here, the monkey can get to his destination where the processes in his body are slowed down. And because of this, we're going to think that 10 years have passed. But he would say that it hasn't. And so by the time he gets there, much less than 10 years have passed. And one other explanation for this is time dilation. So time is shortest when you're in your own reference frame. If we believe that the monkey reached his destination in 10 years, then we're measuring it actually longer than it really was in his frame. He's going to say that much less than 10 years have passed.